and he actually did most of the heavy lifting and programming related to this presentation. And if this conference would not have coincided with Marble, he might have presented it myself. So even though I do work for Ethereum right now, I'm wearing my academic hat. So this work was supported by Budapest University. Chris Buckland, who did the state channel implementation, about which I'm going to talk a little bit in more detail later, and Peter Burci, also from our department at Budapest University. So why do we need privacy on the blockchain? So this is a privacy preserving or privacy enhancing technology that I'm going to present. And even though some people say that you did nothing wrong, you have nothing to hide, but I would beg to differ. First of all, if you're using cryptocurrencies and you pay at a coffee shop, then the barista will actually know how much money you have, which is not necessarily what you want. But the barista actually knows more than that. So if you've ever supported this guy, he published a Bitcoin address, and you might have transferred some Bitcoin his way. And at some point, it became a felony to support him, at least in the United States. And moreover, the barista will know. So if you pay at the bar or at the coffee shop, the barista can actually check whether or not you have contributed to this guy. And finally, it also is quite fundamental to the fungibility of the token, that it's untraceable, because if the entire history of the monetary unit with which you're paying, the particular one, is knowable, then suddenly 1 Ether will not equal 1 Ether, because the willingness of people to accept your payment will depend on its history, or might depend on its history. So in this regard, paper money is better because a paper bill is indistinguishable from another paper bill. So we would like to bring about that kind of property of paper bills, that they are indistinguishable from another, and when you're receiving payment, you don't need to worry about what happened to that particular note in the past. So that's the motivation for our work. And so this is from the Twitter of István, who is my student and worked a lot on this project. And you can see that people actually do understand that on Twitter that it actually is a important topic to have privacy on the blockchain. So let's do a little bit of overview. So the year 2018 was a very productive year in terms of privacy enhancing technologies on the blockchain and in the cryptocurrency space in particular. So we have Monero, which so it's been around for a while, but they have implemented in 2018 bulletproofs, which are a very gas efficient, or in their case, just computationally efficient variety of zero-knowledge proofs, which brought down their transaction size from 18.5 kilobytes to 3 kilobytes, and the transaction cost from 80 cents to about 2 cents, which made Monero far more practical than it was. And we also have Zcash, which in 2018 introduced sapling, which took down transaction creation time on a computer from 40 seconds to 3 seconds. So it actually became feasible to do Zcash transactions on mobile devices. And the RAM requirement went down from 3 gigabytes to 40 megabytes, which again enormously widened the assortment of devices which are capable of creating Zcash transactions. So both Monero and Zcash became far more practical in last year. And what we did is kind of contributes to this same trend. But before I go to the details, let me introduce some basic notions about blockchain privacy. So it usually means two distinct things. and we're interested in both. One is anonymity, namely that when you receive a payment, you don't know where it came from, or you don't have to know where it came from. And the second one is confidentiality, meaning that observers of the blockchain, so the blockchain is a public record, everybody has access to the blockchain, and yet what we want to keep confidential is the amount, the details of the transaction. So where it came from, where it went, and what the amount is. And in particularly, when we distinguish between anonymity and confidentiality, usually anonymity means the sender and the recipient, whereas confidentiality means the amount. And if there's and the kind of currency maybe in which the payment happened, but that's not usually part of it. So we're aiming at both here. Traditionally, anonymity is achieved with coin mixers. So what coin mixers do is that a bunch of people deposit their tokens into the mixer runs its course, and then everybody who put a coin into the mixer takes a coin out, and then nobody knows who had which coin, and the larger the set of participants in this coin mixing is, the larger your anonymity set is, the so-called anonymity set, so the set of people of whom you might be one. Confidentiality on the Ethereum blockchain is championed by this project called MixEth, which aims at hiding the details of ERC20 or Ethereum transactions. So with these two technologies together, you can achieve both anonymity and confidentiality. And from now on, I'm going to be concerned with anonymity. And what I present is actually a trustless coin mixing service for Ethereum. So this is not the first one. There are others, but let's see how a coin mixing service works in general. So what it does is there's a number of participants who contribute to the tokens. They are the senders. And then there's a set of recipients, which might be the same set or might be different. It doesn't really matter. And there's a random permutation between them, like it's not, the two cannot be linked. So what the coin mixer does, it breaks the link between senders and recipients, making the transactions untraceable. So what if the coin mixing service is done in a centralized fashion? So in that case, you need to trust the service operator because you are in many ways at their mercy. You need to trust them not to reveal the actual match between the senders or recipients. You need to trust them to actually perform, so to do a fair mixing, not to steal your coins, and so on. So what our threat model is, so we would need to maintain a measure of anonymity even if k-2 senders and recipients are compromised. So if there's another honest participant in addition to yourself, then whether you two swapped coins or haven't swapped coins should not be knowable, even if all the other participants collude. Of course, you cannot do better than this, because if you're the only honest participants, then everybody else who colludes against you knows everything anyway. Well, so this is a fairly ambitious security objective. So this is basically an illustration to it. So if there are only two honest participants, the green and the blue guy in this picture, then even though the red guys know everything, what they do among each other, they can still not know which of the senders corresponds to which recipients. Theft prevention meaning that nobody should be able to take out more than they have put into the mixer. And availability, meaning that no matter what other participants do, you will always be able to withdraw if you have deposited. So those who deposited will always be able to withdraw no matter what other participants do. So there's some previous work. One is Möbius, which is based on ring signatures, just like Monero. It has an important property that the complexity of withdrawals is linear with the number of participants, which means primarily gas cost in case of Ethereum. Complexity is measured in gas. And because of the actually high gas costs of withdrawal, the anonymity sets are quite small because they can easily fill up the entire block. The other previous work that we considered in our paper is MixEth, which is based on Merkle trees and the zero knowledge proofs, ZK snarks in particular. It has a trusted setup as everything ZK snark related, meaning that people who participate in the creation of the initial parameters of the ZK snark, at least one of them needs to be honest, because if during this trusted setup the so-called toxic waste, which is some data that is created during the trusted setup, is not reliably destroyed, then the zero knowledge proofs can be forged. So it has constant transaction costs, both for deposit and for withdrawal, which is a great advantage, but the problem is that these costs are huge because of the verification of the ZK snark on chain. So what our objective is to create a mixing protocol that does not require any trusted setup. You don't need to trust us or anybody else. So it's entirely trustless in that respect, and is gas efficient in the sense that you don't need to spend as much gas as with the other solutions. So the cryptographic primitive that we use is the so-called NUF shuffle of public keys. So this has been around for, I think, about 10 years now, maybe even more. So this is well established and well understood cryptography. So what you do is you take a number of public keys, which are generator elements multiplied by the private keys, and you multiply them by a secret scalar, C in this notation, and then you permute them. So this is a NUF shuffle. So you start with one set of public keys, you end up with another set of public keys, but because you also publish the generator element multiplied by the same constant, anybody who knew the private keys of the previous set will also be able to find their own public key in the shuffle. Namely, they take the generator element, which is up there in the top right corner, and multiply it by their own private key, and that will be their new public key, and then they can check whether whether their own public key is in the shuffled set actually. And you can actually provide a zero knowledge proof that shows that you have actually included all the keys and in general done the shuffle correctly. Or if you don't, there's another thing that can be zero knowledge proved, namely that your key was not included in a shuffle, which is a much shorter zero knowledge proof. So you can do this both interactively and non-interactively. And the only cryptographic assumption on which this whole thing rests is the decisional Diffie-Hellman assumption. Everything else is unconditionally secure. But the problem is that verifying the entire proof on chain is quite expensive. So the current implementation is a interactive version where if everything goes right, then you don't prove anything, and you only prove fraud in case it happened. And in that case, what you can do is you can simply find out which of the participants did a incorrect shuffle, and you can take their coin. So what you do is you first commit to the shuffle. So the guy who wants to participate in this protocol deposits their coin, submits their public key, does the shuffle, submits the generator of the shuffle, and then all the participants, or all the other participants who are watching this, they are going to check that, okay, their public key is there, so everything is fine, or there's something bad going on, so there's a A6 corresponding to no known private key in the beginning, and poor participant number 4 cannot find their own public key among the shuffled keys. So in that case, he can simply submit a cheap zero-knowledge proof that proves that this shuffle was done incorrectly. We punish whoever submitted that particular shuffle, and we disregard it, we discard it. So basically, we exclude and punish dishonest participants. And we can do the whole thing on a state channel off-chain, which is even cheaper than that. And this is due to Chris Buckler, who has implemented this using the counterfactual framework, which means that the withdrawal is spending the state channel's funds to the recipient address, and the shuffling happens off-chain inside the state channel. So here's a bit of comparison with the other work that we have done. So as you can see, MixEth currently is a bit pricey to deploy, but that only needs to be done once, and we haven't yet optimized it to the extent that all the other have been optimized, so this might improve in the future. Although with the state channel implementation, you can see that even the deployment costs are very competitive with other solutions. Deposit, again, is, well, it's kind of within the same order of magnitude as the others, and in particular much better than Maximus. But with the state channel, again, this is cheaper than any other solution. Now the shuffle, there's no shuffle step in any of the other protocols. So if we do the shuffle on chain, then it has some extra gas cost, as you can see, which depends on the number of participants. So there's a shuffle upload cost, which is linear with the size of the shuffle, and there's a challenge cost in case the shuffle was incorrect, which is constant. But that only occurs if there was some fraud. So actually, it's just a deterrence. It doesn't happen. It's not supposed to happen. And there's the withdrawal cost, which again is constant and is much lower than in all the other solutions. So we have actually managed to build something really gas efficient. And as I said, this was built just quickly for the sake of a timely publication. This has not been like carefully optimized for actual use. So there's a lot of room for improvement. Yes.
N is the number of players in your contract?
N is the number of players currently in the anonymity set. So the way this works is that, okay, so with the state channel, the current implementation has rounds. with the Ethereum contract, actually there are no rounds, so at any point people can come and deposit coins, and those who have deposited, they can shuffle if they want, it's not even mandatory, and those who have deposited earlier, they can withdraw at any time. So the size of the anonymity itself can change over time, and whatever the current size is, that's the cost of that's n in the shuffle, because the bigger the bigger the anonymity set, the longer the shuffle that you need to upload. And there's actually a very interesting attack that we have discovered earlier. So if you read older versions of the paper, it's not dealt with. Namely, that if you do so suppose you want to cheat. So you want to know the link between the depositors and the withdrawers, and somebody has shuffled, some honest participant, and you don't want to lose track of who is doing what. And so what you can do is, instead of using their shuffle, you can use an earlier shuffle, which was created by one of the colluding parties. And you shuffle starting with that shuffle. And in order to deal with this, what you need to do in order to prevent this kind of fraud, that you disregard an honest shuffle and just continue from a compromised shuffle, is that in addition to the shuffle, you need to submit a zero-knowledge proof that your generator element and the generator element of the previous shuffle, you know the corresponding secret coefficient C. So you can actually prove that. It's a very simple zero-knowledge proof of knowledge, but it's not included in these estimates. So this table comes from an earlier paper, and because of that, the shuffle upload is actually a little bit more expensive, but it's more expensive by a constant. So the linear costs remain the same. It's just that the constant is a few thousand gas more expensive. So here's another table which kind of shows you the communication overhead of the various mixing services. There are not only Ethereum-based services included here, but also things on other blockchains, Bitcoin in particular. And there's also the centralized versions, which have the kind of trust problems that I highlighted. And as you can see, that in terms of communication overhead, the state channel, both MixEth, on the on-chain MixEth, and the state channel MixEth, written by Chris Buckland, they compare quite favorably, which means that basically at this day and age, there's no justification and no reason for using centralized services. They are basically obsoleted by cryptography. So here are a few references which can help you understand our work and related work. The Twitter account is not mine, so this is Istvan's Twitter account, and as I said, he is the actual developer of the Solidity code of the contract, and he is going to maintain it, and it will be his Twitter where any improvement will be announced, and we are hoping to improve on it because there are many opportunities for improvement. So the code can be optimized, there will be some front end, and we can also add, so there's a very new cryptographic development, it came out last year, that you can use bullet proofs for proving shuffles, which means that we can get rid of the requirement that all participants need to keep a careful watch on what's going on, and that will make the setup trustless and not require constant online presence by those who have funds in the mixer. So basically what you can do, you can submit funds to the mixer, you can keep your private keys, then the mixer keeps working, and whenever you need the funds, you just withdraw them. And in this case, you can have the benefit of a very large unlimited set of everybody who used the mixer in the meantime. And you don't have to be online because you don't have to watch that your funds were not stolen by a dishonest shuffler, because the bulletproof will take care of that. So no shuffle can be uploaded which misses some some public keys. So that's the next step that we want to take, to include bulletproofs of shuffles. So this concludes my presentation, and if you have any questions, I will be happy